Hi everyone, welcome to the third lesson for topic 4.1 forces and equilibrium. So in the previous lesson, we have learned about the first one is how do we find resultant force. So we learned how to draw a force diagram, then after that how to resolve into the different component, and after that by using Pythagoras theorem to actually find the resultant force. Okay, then after that in the second lesson, we talk about forces in equilibrium. So meaning that we are actually identify the situation where if let's say the forces is in equilibrium, so which means that the sum of the components in any direction will be zero. And by using this concept, we try to solve the equation. Okay, so in forces in equilibrium, we also talk about the triangle of forces and also Lami's theorem. Okay, so in today's lesson, we are still going to talk about forces in equilibrium, but in one special kind of situation, which is called as tension. Okay, so yeah, when you are looking, the question today is still much about forces in equilibrium. Okay, so for tension, we are going to apply Newton's third law. So that's why the learning outcome of the day is to use Newton's third law. Yeah, but also we are trying to use the knowledge that you have learned previously as well. Okay, so because of today's lesson, it will be involving the concept of mass and weight. So that's why the learning outcome actually include parts of 4.3 Newton's laws of motion, which how to use the relationship between mass and weight. And because of mass and weight actually involve Newton's second law, so that's why in today's lesson, might as well I'll just introduce you all the law. So that's why I think it'll help you to understand better for the whole idea. Yeah, I'm not sure why Cambridge arranged the syllabus like this, but I believe that perhaps in forces and equilibrium, you are actually applying Newton's law of motion, but then all the motion that we try to apply here is that the acceleration is zero. So meaning that the situation that we are looking at is basically the particle at rest or like moving with constant velocity, but there's not so much of it. It's basically like they are at rest, meaning that they are in the equilibrium state. Yeah. But then in some of the case, we still need to apply Newton's law of motion, for example, like today's lesson. Okay. And for the 4.3, the topic 4.3, which the what is that called, the topic name as Newton's laws of motion. Basically, we are still going to look at Newton's law of motion, but in the case where the object actually has like extra forces, meaning that it's not in equilibrium. So there's like extra forces that actually cause the motion of the particle. Okay, so I hope that you can understand like the whole idea of it. Okay, so now let's move on to the introduction. Alright, so as you look through the handout, you'll realize that for today's lesson, the notes part is longer compared to the normal lessons that we have. So which means that there will be a lot of like new concept and new terms that introduced to you so that you can understand the idea better and to help you actually understand the question when you try to attempt it later. Okay, all right, so let's start with Newton's law of motion. Yeah, so I'm going to add this in your handout. Sorry, I think I missed it up for my first draft here. Okay, so there are three main Newton's law of motion. So Newton's first law tells us that an object will remain stationary, okay, or continue to move at a constant velocity unless it's acted by an external forces. Okay. All right. Yeah, I think as simple as that. So meaning that if let's say there's no external forces that acts on a object, then the object will just remain stationary or continue to move at a constant velocity. Okay, so Newton's first law of motion is basically an observation. So which means that yeah, you'll be able to I mean there's nothing to tell you that what is the relationship between the force and the motion. So basically it's just an observation tell you that if no forces, then the object stationary or moving at a constant velocity. Okay, so for Newton's second law, it tries to actually explain a little bit about the first law. Okay, so Newton's second law expresses how a force relates to the motion of an object. So for an object for constant mass, right, the force acting on the object is equal to the product of its mass and also acceleration. All right, so when you try to look at this, right? So, okay, let's try to continue this first before I explain it. So, the force is measured in Newton. So, 1 Newton is also defined as the amount of force that required to actually accelerate 1 kg at an acceleration of 1 meter per second square. Okay, so because you can see force is equal to the product of the mass and acceleration, so which means in another words, F is actually equal to ma. Okay, when you look at this second law, right, some books actually write that the force acting on the object is proportional to the product of the mass and acceleration. Yeah, but the proportionality is just one, so basically it's the same thing when we try to say it's equal to lah. Okay, so F is equal to ma. So 1 Newton is actually equal to the mass multiplied the acceleration. So which means it's the force that required for you to actually cause the motion of 1 k of the mass of 1 kg in an acceleration of 1 meter per second square. So it actually tells you about first law of motion because there's no force, so that's why there's no acceleration, and that's why the object will remain stationary or continue to move at a constant velocity. Okay, so one application of Newton's second law is the weight of the object. So we know that mass is a measure of the amount of matter in an object. So I hope that you still remember this in like the science thing that you have learned perhaps in your primary school. Yeah. So mass measure the quantity of the matter regardless the location in the universe or the gravitational force applied to it. So which means that no matter where you are, so the object of the mass is always constant in all the situation. Okay, so which means that mass actually tell us that the exact amount of the matter in an object. So it will be measured in kilogram. Okay, so yeah, I mean, we always like misuse this. For example, when we try to measure our weight, right? Actually, we always try to use the unit of kilogram. Yeah, but actually, it's not correct in terms of like science, right? Okay, so weight on the other hand is actually the force of an object due to the gravity. So that's why it's different from the mass just now. The value of the weight, right, will be different, depends on the location. So for example, the gravitational force in on the earth and on the moon is certainly going to be different, right? So that's why when you try to measure your weight in different location, that will give you different value. Okay. So because of that, since we know that force is equal to mass multiply acceleration, so that's why since weight is one of the force, right? So when we try to calculate our weight, it's basically equal to the mass multiplied by what's the acceleration that caused by the gravity is the gravitational acceleration that we have learned in chapter 1, right? The vertical motion. So it's g. Okay, so I hope that you still remember G is basically 10 here lah. So if you, yeah, not sure that you can just write down. G is 10 meter per second square. I mean, it's 9.8 blah, 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 blah. But in maths, we try to just round it to 10 for a easier calculation. Okay, so and it is measured in newtons also because it's one of the force as well. So, and alright, so for an example, a body of mass 20 kilogram will eventually have a weight of 200 Newton. Simple as that. Alright, so I hope that you can understand this idea because later when we try to attempt some of the question, they will try to use mass instead of like the weight. So that's why you will need to know how to convert between them. Okay, so now we are moving into the third law. So Newton's third law states that for every action, there is an equal and opposite reaction. Alright, so for example, if let's say there's a car that actually parked on the street, so the car uh, I mean, the force that is very obvious to us is like the weight, right? So the weight is actually acting downward. So this is like the weight, which is equal to mg. All right. So this equal and opposite reaction. So eventually to make sure that this car doesn't disappear, so that's why there will be a reaction that going up. So this is like the equal and opposite reaction. So this equal and opposite reaction force is called as the normal reaction. Okay, and because of it's opposite of the weight, right? So it should be equal as well. So it's also equal to W equals to mg. Okay, so we won't be looking at that much of the part for the normal component first. So we'll be looking at it when we try to learn friction in the next chapter. Yeah, but for you to understand, the idea is that for every action, there will be an equal and opposite reaction that occur. Okay, so this is very important as we move on to tension later. Okay, so now let's try to look at the focus of the day, which is tension. All right, so I hope that you can spend some time to actually just understand it. I think it's pretty easy lah. So first law is that the object remains stationary or move at a constant velocity unless you have an external force. So second law apply, second law express the force, so which means the force will be equal to the mass multiply the acceleration. Third law, for every action there's an equal and opposite reaction. Okay, just like that. So now let's look at tension. Alright, so tension is actually one of the application for Newton's third law. So for an example, I'm trying to explain it by using this diagram here. So when a boy uses a rope to pull a box, the forces with which the box pulls on the boy is actually equal and opposite to the force where the boy used to pull the box. Okay, so let me try to explain it again by using this diagram. So let me try to use a different color to represent different thing here. Okay, so we have this boy here, right? So this boy is represented by the red color here. Okay, so what is this boy is doing is actually pulling the box, right? So you can imagine that the forces goes like this. Okay, so it means there's that forces that actually exerted on the box that actually the boy is pulling. Okay, so now let's try to look at our second object here, which is the box here. So it's the blue color here. Okay, so because of for any action, there will be an equal and opposite reaction. So that's why when this boy is trying to pull the box, right, the box will eventually try to pull back as well. Am I right? So uh this is the force that actually exerted by the box here. Okay, but now don't forget that there will be another force in between here, which is the rope that the boy is actually using. Am I right? So by using the same idea, when the boy is actually trying to pull the rope, right, there will be a reaction that actually going equal and opposite of the force of it as well. So this is going into the rope. So this is the reaction on the rope. Okay, so same thing. If let's say the box is trying to pulling towards the direction of the box, so which means it will try to exert another force that going in as well. All right, so these are all based on Newton's third law. So that's why you can see that there's a force actually acted on this rope, and this is called as tension. Okay, is that all right? Yeah, I hope that you can roughly get the idea. So the force in the is the tension in the rope. So tension will always act inward. So which means that when we try to say that tension occurs, right? So which means that the tension will eventually moving towards the center. So that's the idea. So we'll be looking at two cases, or if let's say we try adding pulley, then it will be three lah. So around three cases of tension. So tension as is in the first one is the rods. So you can just imagine it's like a rigid connector with no mass. So which means like for example it's like this. So you must remember for a rod it's different than when we talk about a rope or a string, right? Because a rigid connector meaning okay, for example, a simple idea is that you can imagine like a pencil you used to connect two things. So you wouldn't be able to actually stretch, or you wouldn't be able to change the direction of the pencil. It will just eventually to be like rigid and solid like that. Okay, so that's the idea. So there are actually two cases in rods. So the first one is if let's say we try to pull it, right? So that's an idea of pulling it. So it's the same thing. You can try to imagine you hold a pencil at the two side and you try to pull it. Okay, so what happened is that the pencil will actually react and create a force that is opposite and equal to the pull. So which is inwards here. Okay, so since this is a force that actually moving inwards to the towards the center, right? So this is called as the tension. So that's tension that actually occurs in the rod. So this is basically it's like the what is that? The forces is actually pulling inwards. Okay, so we have this second direction. So same thing. Imagine you try to hold a pencil on two sides. So when you try to push the pencil, so what happened is that it will actually cause a thrust. Okay, so let me try to do like this first. So the forces are actually going in, right? So that's why it will create a force that actually reacts oppositely. So it's going to be like this. So this is not a tension because it's not act inward. So this is called as a thrust. Okay, so the forces is actually pushing upwards. So in today's lesson, we are not going to talk about that much of this, but for you to have an idea is that you might imagine that tension is easy because if let's say you are using the connector to actually pull something like there's a car here, then you try to pull a trolley here, then it will always be in a tension, right? Because you're trying to pull it, so the trolley will actually forms another opposite forces, so that's why it creates tension. But how about thrust? So you can imagine that something that you are just trying to pull it as well, but as it stops, right? If let's say the car here stop, it will eventually create a push force towards the connector. So that's why it's going to be another push force from the trolley as well, and it forms the thrust. But for today's lesson, we are going to look at tension part. Okay, so this is the rigid connector, which is basically rods or even things like they try to use like the metal bar and so on. So it's a rigid connector. So the second part that we are going to look at is string. Okay, so string meaning that any rope, any chain, wire, cable that you can actually change their direction basically. Okay, so for string, right, you wouldn't have the idea for truss lah because it's not rigid, right? So that's why there's two main situation for string. The first one is if let's say we try to use the common words that we have, then this is like the tight one, okay, the tight string. So but in max, right, this is called as taut. Okay, so which mean it's simple means that the string is tight. Okay, so we will say that it's taut, so that's why the tension as is here. So this is the words that you will be seeing later in the some of the question. So this one you can see that if let's say there's no, this is like a loose string. So in max we call it as slack. Okay. So for the situation where there's slack, right, you can imagine that there's no tension actually as is in the string. Okay, so there's two main difference between the rods and the strings that we are discussing here. So first one is a string can change direction. So meaning for example, when we talk about pulley system later, so which mean that this, if let's say this is a pulley, right? So the string can actually change direction, meaning like this. Okay, then it will just create like the tension over here. So that's the idea of can change direction. But this one is like a rigid connector, right? So that's why you cannot actually stretch it or you cannot actually reshape it. So that's the idea. Okay, so the force in the string can never be thrust. So similarly, the force in rod can never be a slack as well because you can like the rigid connector will not be like loosened. You get what I mean? Then after that, for a string, as there's no tension, then that would be slack. That wouldn't be thrust happen. Okay, so that's the idea. Because when you try to push it inwards, that basically create a slack is not a truss, right? Because the rigid connector is not, I mean, because of the string, it cannot be stay in the same situation like the rods when you try to push it inwards. Okay, so another two words that you will always see in the question is that to because of we want to keep the calculation simple in mechanics one, so that's why we'll always try to assume that our string is light. So you always see this word. So meaning that the weight of the string can be ignored. So the idea is that you can imagine, right? If let's say this is a string, so if the string isn't light, right, so it has certain mass. So which means when you try to look at the tension at this side, so yeah, maybe this is like a string. So you can imagine that because of F is equal to MA, right? So in practical, so we know that the mass of the string at different parts wouldn't be the same. Like for example, maybe here is like a little bit higher than here. So that's the idea. So if let's say the weight is taking I mean if we try to take into the consideration of the weight, right, or the mass, then which mean that at different point of the string it will just create different tension. But in this case we always assume that the string is light, so that's why there won't be any weight involved. All right, the second thing that you will see is the words called as inextensible. Okay, so we know extensible, right? So meaning that something that you can, stretch it, make it longer or make it shorter. So this is the word like inextensible. So meaning that they cannot be stretched. The stretch in idea is that it cannot become longer or it becomes shorter lah. So it's not elastic in a way. Yeah. So that's why the length of the string is always a fixed one. So you cannot like because of you like you can actually pull it like very hard so that it become longer and so on. So this kind of situation wouldn't happen in mechanics one. So basically all the string that you will be looking at is the light in extensible string. All right. So now before we move on to the question, we'll be looking at one last idea here, which is the pulley system. So a pulley is a wheel over which a string passes. So this is like the string, so this is like the pulley. So normally in all the question that we will attempt later, the pulley will be in a smooth trolley. So a smooth trolley meaning that there's no friction in the bearing. Okay, so no friction in its bearing. So for a smooth pulley, right, so you can imagine that this is the same string that goes over. So that's why, okay, let me try to do it like this. So you can imagine that these two will eventually create a weight, right? So this is weight one, this is weight two. Okay, then after that what happened here is that as you have the weight, so the rod will actually create an reaction that's opposite of the force here, of the weight here basically. So it means that we have the tension here. So because this is the same length, so that's why the tension here will be the same as well. Okay, so because this is trying to moving inwards to the rod, so that's why you can imagine that there will be another opposite reaction here, and this will form the normal reaction here. But we don't talk so much of the normal reaction of this thing. We are just going to focus on this part. So meaning that the weight, then there will be tension going upwards, going inwards towards the center. So for a smooth trolley, you must remember if you are using the same string along the pulley, right? So that's why the tension will always be a constant. Okay, so yeah, you just remember that because it's a light string, so that's why as long as you are using the same string, so the tension will be the same. So if let's say you are using two different string in the same situation, then you will be having two tension. So that's the idea. So we'll be looking at 5 example later. So the first two one will be the easier one, which means you are given like the direction of the tension already. So you might not need to really care so much about the drawing. But for the later part, we are going to look at the harder question. All right, so let's move on to the example. All right, example one. So this is a pretty simple example. It's basically just similar like your previous question. It's just that now the tension is involved, but basically they give you everything already, so it doesn't really need to draw the force diagram by yourself. Okay, So yeah, that's the idea. So mass of the 10 kg here, all right, is suspended in equilibrium by two. You can see the words here: light inextensible string A and B, which actually made up the angle of 15 degree and 35 degree respectively to the horizontal. Okay, calculate the tension in the string. So that's why they are equilibrium and the forces are all actually acted on this point, right? So that's why we just try to do the resolving and we try to solve the question. So this is a very straightforward question actually. So let's start with the horizontal one maybe. All right, so we have here this is the tension for A, right? Okay, so we can just try to write this is tension. Oh, okay, maybe we can just let A be the tension for string A. All right, then after that, the B is the tension of string B. Okay, so that's the idea. So now let's try to do some resolving because you are given also, which means we have the tension of the rope here and here. All right, and this is the weight that created by the mass. Okay, so something that you might want to be very careful is this because you are given like 10 kg. I'm sorry, this is 10 kg. So yeah, it's not 10 g here. So it's 10 kg. So which means in this form, then we might need to actually change the mass into the weight first. Okay, so the weight in this question will actually just be 10 multiply 10 lah. Yeah, because 10 g. Oh, right. I think the 10 g here, the g here isn't the unit. The g basically means that it's the gravitational force here. So it's like 10 times 10 and it gives you 100 Newton. Okay, so now we can try to solve the question. So resolving in the horizontal direction. So we have our left hand side, we have the tension of A cos 50. Then after that equal to B cos 35. Okay, just like that. So because we are not solving the angle, so I think it's helpful for us to just change it over. So later we can try to do substitution. So 35 over A cos 15. Okay, so this is the first one. All right, then after that, let's move on resolving the vertical component. So it's just the same thing like how you do your forces in equilibrium for this question. So we know that this will be 100 Newton, right? Then it will be equal to A sine 15 and then plus B sine 35. All right, so this is our second equation. So now we try to substitute our first equation to the second equation and see what happened. Okay, I think you should be quite familiar with this already. So I'm just going to work out the working, then you can check your answer after this. So, oops, I'm sorry, I think I made a mistake here. So yeah, leave the A here. So there's no A here. All right, so yeah, let's check it through. All right, so I hope that you can get the answer. I think it's pretty straightforward. Lah. Just type in everything in your calculator, then you should be able to get your answer. Okay, so let's move on to the next example. All right, so the next four questions were all from the past year questions. So I think it's good that we can try to go through first before you try to attempt the questions in your exercise. All right, so if let's say you're confident enough, then you can just try it out. Then you check your answer also before you try the question lah. Yeah, because I guess it will be helpful for you. Okay, so yeah, for this question, a block of mass mkg is held in equilibrium below a horizontal ceiling by two strings. So this is a two string as shown in the diagram. So you must remember that there's two string. So that's why the tension wouldn't be the same, right? So that's why when you are looking at this, the tension here is T and the tension here is 20. So one of the string is inclined at 45 degree, all right, and the tension of the string is T, then the other one is 60 degree and 20 Newton here. Okay, so that's why the question wants us to find the T, what's the tension of the string here and what's the mass of the block here. All right, so which means what we have here is we have the weight here as well. So that's why in this case, what we know is this is the mass, right? So the weight that actually apply here is actually 10 m lah, because we have mg, so that's why 10 times m. So you might want to just remember this in your question, that you are not only using m here because this is the mass. All right, so instead you should be using your weight. Okay, so now I think this question is still okay. So what we try to do is we try to resolve it. So this is the point where all the three forces actually exert. So that's why you can imagine that later we are going to resolve it at this point. So what we can try to do is we can try to draw a straight line here. So it will be easier for you to understand it. Okay, so yeah, this is like the horizontal line. So that's why you can imagine that if let's say later we want to solve the question, right, isn't it we need the angle here. So that's why this is a vertical, sorry, this is a horizontal line. So this is why the question is important to tell you that this is a horizontal ceiling. So that's why this is horizontal. So as we try to resolve it to the horizontal component, so we can see that this forms a Z. Okay, so the parallel idea. So that's why what we have here is a Z here. So this is 45 degree. So similarly, is another Z over here. So that's why this is 60 degree. All right, and now we can try to resolve it. Okay, so let's try to resolve in the x direction first. So for the horizontal component, yeah, because we if we try to solve that first, so meaning we only have one unknown in the equation, right? So that's why we have this tangent, sorry, we have this tension, yeah, tension cos 45, and it will be equal to 20 cos 60. All right, so the weight is in the vertical component only. So by having this, then now we can solve our tension already. So it's 10 square root 2. So you might want to write an answer in QSF. So you might want to keep the exact value for your calculation later. Okay, so yeah, you doesn't write t is okay as well, because this question they already give tn, right? So that's why it should be a value only. Yeah, but if let's say you try to write and there's nothing wrong as well. Okay, so now let's move on to the vertical part. So we try to resolve it in vertical. So we have the weight here. It will be equal to our tension sine 45. Okay, and then plus 20 sine 60. So let's substitute the number that we have. So weight equals to mg, right? So the m in this question is m. Then after that, 10 is the g. So that's why we have 10m. Then it will be equal to 10 square root 2. Okay, sine 45. And then plus 20 sine 60. So you can just use your calculator just to solve everything. And you will be able to get your m here, your 10m here will be equal to 10 plus 10 square root 3. So when you try to solve it, and you'll be able to get 1 plus square root 3 in exact value. Or if let's say you want to change it to QSF, then it will be 2.73 in QSF. Okay, so I hope that you can understand better the idea of the tension here. This is a question that's pretty direct also, because you haven't got anything that's like perpendicular or any angle that you need to solve yourself. So basically it's just a simple Z for you to realize, and for you to actually get that you need to resolve everything in this point. So that's the idea of this. Okay, so let's move on to example 3. All right, so the next question. So yeah, you can see the question normally it will be quite long, so it's important for you to understand the idea, so that you can use every information that's given in this question to help you to solve it. Okay, so this is a smooth ring R here, all right, of a mass mkg. So that's why they are telling you smooth, because to indicate that there's no friction that actually occur between the ring and also the string. So it wouldn't be actually affecting each other in a term of forces there. Okay, so it's threaded on a light inextensible string. So you can try to see this is the no mass and then cannot stretch the string also. So yeah, but the important thing that you see is that this is a string ARB. So that's why ARB is actually one string, it's not two. Okay. So the something that you might actually write it here is that the smooth ring has a mass of mkg. So that's why there should be forces of weight going down. So the weight here is going to be like another 10 m as well. Okay, so yeah, because of the mass is m, so the g is 10. Then after that is on the same string, right? So that's why there is a tension that is the same here, which is the T and the T. Okay, so yeah, as you move along, then you try to understand it. Then the end of the string is attached to a fixed point A and B, and A is vertically above. So this is like a vertical line. So the string is taut, so which means it's not a slack one, so there is tension that happen, right? So that's why by having a tension is correct. Then the angle for ARB here is 90 degree. So the angle between the part AR of the string and the vertical is 45, so meaning the vertical and the string, so here is 45. So the ring is held in equilibrium in this position of a force of magnitude of 2.5. So this is a force of 2.5 here. Alright, so acting on this ring. So calculate the tension in the string and the mass of the ring. So basically the M is what we want to find and the tension here. So the point that we want to focus in this point eventually is on the ring here, because this is where all the forces actually meet each other, right? So I think I will show you two ways. So the first one is, if let's say we try to resolve it in the direction that we doesn't need to solve that much, because you can actually see that if let's say we try to resolve it in the direction of 2.5 Newton, right, then the perpendicular is this one. So which means the only forces that we need to resolve is the weight. Okay, so it will be helpful for us to find out what's the angle first. So you can see why the question purposely tell you that A is vertically above B. So is that to indicate you, if let's say this is a vertical line, then the weight it should be acted vertically downwards as well, right? So that's why this actually forms a Z here. So the angle here will actually be the angle here. So what's the angle here? So 90 degree, 45. So that's why this is 45 as well. So this is 45 also. Okay, or if let's say you doesn't want to find here, then it's the same thing like if you try to use the idea of C. So that's why 45, so here will be 135. So 135 minus 90, then you are getting 45 as well. It's just the same. Okay, so now we try to resolve it in the direction of BR. So resolve in direction BR. Yeah, because we doesn't want to find so many value, right? I mean, we doesn't want to resolve so many. So in the direction of BR. Okay, so what we have is on this line, right? So that's why we have this 2.5. Okay, and it will be equal to the, here is like perpendicular towards 2.5. So this tension isn't a matter here, but we have another tension here. So it will be equal to our T, and then plus the resolving for this part, it will be R cos, sorry, it's not R, it's our W here. So W cos 45. Okay, so W cos 45. Yeah, so if let's say you doesn't want to change to 10 m first, it's okay also. You can just move on, solve your W, then only you solve your M. Okay, so by having this, then this is our first equation. Okay, then after that, we move on to the second one, so which means we try to resolve in the perpendicular direction. Yeah, I doesn't want to write so much. Perpendicular of BR. Okay, so yeah, this is going to give me what is on this line. So that's why I have a tension that moving upwards. So that's a T. Then it will be equal to, so the tension here and the 2.5, these two forces are perpendicular to T. So it will create zero forces there. So the only thing is the here lah. Yeah, so which means is the weight here after you resolve. So this is the weight. So W sine 45. Okay, so this is our second equation. Alright, so by having this, I think now we can try to solve our T first, or you want to solve W. Yeah, I mean, it's basically the same. So I think in this case we can try to solve our t first. Yeah, so we can just try to substitute 2 into 1. All right, so okay, this is something that's special. Yeah, because I was thinking it's easier because of this. So when you try to say sine 45 and cos 45 is actually the same thing, right? So we can imagine that if let's say I try to change this into w cos 45. Okay, I mean if you doesn't want to change it, you also can solve it later. Idea is just the same. Yeah, but I'm just going to change it because I just want to substitute 2 into 1. So what I have is 2.5 will be equal to 2t. Okay, it's the t plus t here. Let me try to write in full. So t plus t, so that's why from here then I can get my tension is 1.25 Newton. Okay, so by having this, then now I can solve my W. So from equation 2, then I can get 1.25 is equal to W cos 45. So by solving this, then I can have my W will be equal to 1.77. Okay, so this is in 3SF. Then after that, we know that W is mg, right? So 10m here. So 10 is the G, m is what we want to find. So yeah, then 1.77. So this is how we get m equals to 0.177. So 3SF. Okay, so this is supposed to be kg. Alright, so that's the idea. Yeah, same thing if you didn't write kg is fine also because here the m just represent the value. Okay, so now I'm just going to show you if let's say you want to resolve horizontally, you can do that as well. So I might use different color here so it will be easier for us to see. So similarly, you have the point going down, right? So that's why you have this vertical component. Okay, so as we try to resolve it, so which means that we might need to get our some of the some of the angle that we need. Okay, so I think for this one it's pretty straightforward because you can see this is a isosceles triangle, right? So when I try to draw a line here, so this might form one right angle triangle, this is another right angle triangle. So from that, then I'll be able to get that this is actually 45 and this is actually 45 as well. Okay, then for the weight is the one that no need to no need to resolve it. So then from here, then this is 180, so that's why 90 45. So here is 45 as well. Okay, so if let's say I try to resolve it horizontally, then what do I have? So resolve horizontally, I'll have 2.5. Yeah, so you can see that I'll have this tension cos 45, tension cos 45, then equal to this 2.5 cos 45. So from there, then I think we have only one unknown, then we can straight away solve it already. So t cos 45 and plus t cos 45, and it will be equal to 2.5 cos 45. Alright, so from here then what do I get is I can just straight away 2t lah, so 2t cos 45, then you just solve it. So you'll be able to get straight away write the answer. So you can straight away get your answer as the same as well. Okay, as you try to resolve it horizontally. Then after you get this, so let's try to look at the vertical one. So for vertical one, you have these two above and these two below, right? So yeah, but by looking at this, because you know that this will be t sine 45, sorry, this will be t, yeah, you're right. So t sine 45, and then here will be another t sine 45. Then they will try to eliminate each other, right? Because you can imagine this is 45, this is 45, the tension here is the same. So that's why basically when you try to calculate the vertical, you can just try to ignore that because they will balance out each other. Because you imagine this going up will be t sine 45. Then after that, you will have the other going down is like another t sine 45. So eventually you will get 0 lah. So you might ask how come just now the horizontal cannot, because you remember it's double, right? So it's like both going to that side. So they are not eliminating each other. But for this one, because one up, one down, so that's why they are going to eliminate each other. So what we have is only this part. So we can straight away if we try to resolve it in the direction of y, so what we have is the weight will be equal to 2.5 cos 45. Okay, so similarly, I can straight away solve it because I have only one unknown, which give me 1.77. So same thing, my mass will just be equal to 0.177. All right, so yeah, that's the idea. So I hope that you can understand it. Okay, so now let's move on to the number 4. All right, number 4. Okay, so yeah, so when you try to look at this, then it's about string as well. All right, but something new to this is that you are not given any angle here. So yeah, and you need to identify the tension, the direction by yourself as well. Okay, so we have A and B are fixed point of the vertical wall. So similarly, they tell you that they are on the vertical line basically. So A is vertically above B. So the particle P of the mass is 0.7 kg. So that's why you have this weight going down here. Okay. So you have W here. So it's attached to A by a light inextensible string of length of 3 meters. So P is also attached to B. So with another string. So that's why you can imagine that these two strings, so because they are different strings, so that's why they will form different tension here. So you can imagine that we will have this one is like our tension 1, then this is our tension 2. Okay, then after that, yeah, so it's attached to B. So P is maintained in equilibrium, so it's equilibrium as well. So at a distance of 2.4 meter from the wall by a horizontal force of magnitude 10 acting on P. So you can see both strings are taut, so that's why because they are taut, so that is there is tension that actually exists here. So the 10 Newton forces acted in the plane of APB, which is perpendicular to the wall. Okay, find the tension in the string. All right, so basically we are getting the tension here, so we can just write down first. So let T1 be the tension of the line for AP. Then after that, T2 be the tension of uh, BP. All right, so by having this, then now we can try to solve it. Okay, so what's the problem that we have here is we don't have any angle. So that's why that's the thing that we need to find it out. Yeah, so as you can see, because this is the two tension that we want, right? So basically we can just get what is the angle here, then that's enough helpful for that's more than sufficient for us to solve the question. So you can see that that's given two length, right? So that's why we can always use our trigonometry knowledge to actually help us to solve that. Okay, so let's try to denote this as O maybe. Yeah. So yeah, if you want to write, then you can just try to let O be the foot, of perpendicular line from P to AB. Yeah, so just to indicate what's the thing that you're actually finding. Okay, so yeah, basically we can find here first, so which means the angle for APO, right? So the angle for APO, okay, so it will be equal to, so in this case, I have my adjacent and I have the hypotenuse here, so which means I can use cos. So cos AH is 2 over 4 over 3. So that's why, oops, sorry, I should write cos. Yeah. Okay, so cost for APO will be just equal to 2.4 over 3. Okay, so by having this, then you should be able to, okay, right, for this question, right, it will be very helpful for you. So this is a question that you can see is very helpful for you to know how to store your value in your calculator. Because you can imagine later I still need to use to solve this. So your answer in your calculator can be the latest one only. Then later when you need this angle, then you doesn't know how to get it back. So that's why you must know how to store your value lah. So I think it's very important in your paper of mechanics. So right, so in this, let's try to do it together. So which means that what do I have is shift cos, okay, and then 2.4 over 3. All right, so after I did this, yeah, let me just write properly. So after I get the value, then what do I do is shift, then store, then I have this store value here, then just store it as my A. Okay, then equal to, so this will be my A. So you can always just check it out, alpha A, then you just press equal to and check whether it's the value that you want just now or not. Okay, so yeah, because when you try to write it out, you cannot actually write so much, right? So that's why it's like 36 point. We try to write false significant as well because to be the form of accuracy, I'm just showing it. Okay, then after that, let's try to get our OPB. Okay, so similarly is A and H as well. So cos OPB, we will have, what is that? 2.4 and then 2.5. Okay, and then we can try to solve it. Okay, so same thing, we try to use our calculator. So now shift cos 2.4 over 2.5. All right, so yeah, this is our B. So after we get the value, then shift store, then we try to put in our VB. All right, so you can always try to check it. So alpha B and check whether it's the value that you want or not. So 16.26. All right, so yeah, you might just want to remember like the first one is A, then the second one is B. So now we can try to do our resolving. Okay, so let's try to do vertical first. Let's try to do horizontal first, I think. Okay, so we have this 10n, right? Then because we can solve, we can have our tension 1, tension 2 first. Okay, so now let's try to look at it. So Rx, let me try to see whether I can oh no, because I have two tensions, so eventually I will still need simultaneous equation. All right, so is 10 will be equal to T1, then cos T2 also cos. All right, so Rx will be 10. The right hand side will be equal to the left hand side. We have T1 is going to be cos 36.87 and then plus T2 cos 16.26. Okay, so now by having this, then we might just want to rearrange it a bit so later we can just substitute and to get our answer. So I think for this question it's helpful for us to just do tangent, so that's why I would just put on my T1 on my left hand side. So 36.87, it will be equal to, so keep this, so 10 minus T2 cos 16.26. Okay, so now I'll resolve in the vertical direction. So just now we have the weight moving, acting downwards, right? So it's given the mass as well is 0.7 kg. So that's why we can just change it here. So we have our mass and then the gravitational force is 10. Sorry, gravitational acceleration is 10. So that's why we have 7 Newton. Okay, so by having this, then now for the bottom part, it will be 7 plus T2. So since we write our T1 in left hand side, so let's start with this. So I have resolved to y direction. So T2 sine 36.87 will be equal to 7 plus, just now is that's T1, right? Sorry, I'm sorry. This is supposed to be T1. Yeah, and then here is T2 and then sine 16.26. Okay, so by having these two equations, then now I can use tangent to solve it, I guess. So 2 over 1. All right, so yeah, I'm just going to fast forward the working as well, but for this question it's very helpful for you to see later. I'll show the calculation, the calculator part also, so you can try to see as we try to keep the value in calculator. Actually, it will be easy when we try to input the number later, especially you have all these what is that called, repeated numbers, so it's very helpful for you to just press A and B instead of like pressing the number over and over again. All right, so let's start with the solving part. Okay, so that's it for the working part. So I hope that you are right solving by yourself with the calculator and the simultaneous equation. Okay, so let's move on to the very last question where we discuss about pulley. All right, number five. So this is a pulley system, but instead of using pulley, they are using pegs, but the idea is just the same. So the idea is for you to understand that string can actually change direction. So for example, things like this can be actually from the same string. So if let's say they are using the same string, which means the tension along the string will actually be same. If they are using different string, then which means that they are different tension. Okay, so that's the main idea that you need to understand. All right, so let's read through the question. So each of the three like inextensible strings, so same thing, the same words that you keep on looking at in this example, so has a particle that attached to one of its end. All right, so we know that the important information here is this is not one string, so there are three strings altogether. Okay, so the other ends of the string are tied together at point O. So this is the point where all the strings are tied together. So two of the strings pass over the fixed smooth pegs, so which means this is the string that passes through, then the particle are all hang freely in equilibrium. So the weights of the particle and the angle between the sloping parts of the string and the vertical are shown, so alpha and beta here, and is given sine beta and cos beta. Okay, so let us try to draw the force that actually exert in this diagram first. So we have the weight here, right? Then eventually we have a force that react in the opposite direction. So that's why I have the tension for this first line here. Okay, so we know that this is going to be the same line because two of the string passes over the fixed smooth pegs. So the string actually tied together here. So this is like the first string, the second string, and also the third string. So that's why I will have tension going up. So this is the pegs, right? So eventually it will have a force that react oppositely as well. So this is the tension cause. So that's why this is going to be T1, T1. So similarly, the string is tight here. So that's why you have a force that cause a tension over here. Okay, so this is how is that going to look like. But then in this question, we are actually not looking so much at this point because the question didn't give us any information about, any questions that we actually need to find out the pegs part. And we know that the tension will eventually be the same, and we doesn't need to find the normal reaction over, so which means that we are not interested in this part. Okay, so similarly for this one is the second string, right? So that's why I'll have the weight, and also I have the tension for the string 2 here. Okay, then the same thing, the string is tied over here, so it forms another tension here as well, so which is the same tension in string 2. Okay, so this is string 3, so it's just basically the same thing like string 1 here lah. So I have tension 3. Okay, so from the pulley, so T3, T3, and also tightening here, so that's why I have T3 here. Okay, so the part that we will be looking at is actually there are four parts. So I hope that you can see this in this diagram. So first one is that, so we know that all the particles hang freely in equilibrium. So which means that by looking at this part, this part, this part, we can actually get some of the tension. Okay, so this is like the first part, the second part, the third part, and lastly, we'll be looking at this part because this is the part where all the tension meet together, and this is the part that involve your alpha and beta, which is what we want to solve in our part 1. Okay, so show that W cos alpha is equal to 3.8, then the question wants us to find W sine alpha. Okay, so let's try to solve whatever that we can first by looking at these three situations first. So for number 1, so for this particular one, we'll be able to look at the T. So basically you do not have other component, right? So the T1 here will just basically equal to the W that we have. Okay, but the question doesn't want us to find W here, so we can just leave our answer here first. Then after that, we are looking at this part. So there are only two components, one going up is T2, one going down is 8. So that's why in this term, we can actually straight away find our T2 already. So T2 will be equal to 8. Okay, so similarly for P3, T3 here, we have this one. So the forces acted on this particle also only 2. So that's why we can straight away solve that T3 is actually equal to 7. Okay, so now lastly, we'll be looking at this part. So by looking at this question, right, the question wants to solve to show for W cos alpha first. So by looking at this, then we need to determine whether it's the vertical component or the horizontal component. So we can actually solve it in an easy way. Okay, so let me just try to draw a horizontal line. Alright, so by looking at this, right, you should be able to realize that for W cos alpha is basically refer to the vertical component because your alpha is here, right? So if let's say you want to solve for this line, then eventually going here will be T1 cos. So that's why to actually find W cos alpha, we will actually solve the vertical component first. So there are actually three forces that acted here. The first one is the T1 cos alpha, then we have T3 cos beta, then it will be equal to the T2 here. So let's try to write it down. So this is resolving to the vertical component. Okay, so what we have is just write down first. So T1 cos alpha and then plus T2 cos beta. Okay, and then it will be equal to T3. All right, so I hope that you can see it. So basically, we are looking at this part. So three forces, 1, 2, and 3. So that's why vertical component, we have T1 cos alpha, T3 cos beta, and then T2. Okay, so now we can try to just substitute the, oops, I'm sorry, this is T3, this is T2. I kind of like T3. So the vertical one going downwards is our second string. Okay, yeah. So T2 here, then the one that we cos beta is our T3. Okay, so and after we have this, then now we can try to substitute the value that we have here. So we know that T1 is equal to W, right? So W cos alpha, then plus our T3 is 7. So cos beta is given in this question, which is 0.6. Okay, then it will be equal to T2 we have found just now, right, which is 8. Okay, so by having this, then now we can actually see that cos alpha will be equal to 8 minus 7, 0.6. So that's why this is how we get our 3.8. So shown. Okay, so now by using the exact same idea, then we can try to find sine, which is to resolve it in the horizontal component. Okay, so what we have is we don't have any T2 anymore because it's perpendicular. So we have T1 sine alpha is going to be equal to the right hand side, which is, oops, is equal to, apologize for that. So yeah, so it will be equal to our T3 sine beta. Okay, so in this question, so same thing, we want to find W sine alpha. So that's why T1 is W, right? So W sine alpha will be equal to, our T3 here is 7. So sine beta is given in this question as well. So sine beta is 0.8. So 0.8. So from here, we can get our answer. W sine alpha is basically equal to 5.6. Okay, so that's our answer. Okay, so now let's try to look at part 2. The question wants us to hence find the values of W and alpha. Okay, so which I think this is pretty easy lah. So because we have these two equations already. So let's try to write down. So W sine alpha equal to 5.6. First equation. W cos alpha is 3.8. So this is our second equation. Alright, so let's try to solve it. I think we can try to do tangent first. So 1 divided by 2. So we can get tangent alpha will be equal to 5.6 over 3.8. Okay, so from here, then you can solve alpha is equal to 55.8. So in one decimal place for all the angle. Okay, so 1 dp. So yeah, remember to just keep this value in your calculator as well. So yeah, you are just pressing W cos and answer later. Okay, so we can use number 2. So W cos 55.8 will be equal to 3.8. So from here, then you'll be able to get your W and write in 3SF, so 6.77 Newton. Alright, so by having this, then we solve all our questions here. Alright, so I hope that you can try to understand the idea for tension. So for the exercise for today, it's basically about tension only and it's in equilibrium. Alright, and in the next lesson we'll actually learn about friction. So after this, then it will be all about friction. Then after that, we'll move on to the next chapter. Alright. So I think now you can actually started to do some revision for your M1 already. So I mean, instead of you have everything that you want to do your revision before your test, right? Okay, so yeah, that's the whole lesson for today. So thanks.